Alright, so it's been a little bit, but I'm going to post a couple more videos before my semester starts. I've been, taking care of school stuff, and obviously with the coronavirus, a lot of stuff's kind of in the air right now for my kind of education, at least immediately. But anyways, there's a couple problems worth doing, so I'm going to go ahead and do some. The first one is energy in a boomerang. So it says that we have this person that throws this boomerang at a certain velocity, at a certain angle from the horizon. It tells us how much it weighs. It's rotating at a certain revolutions per second. It gives us the moment of inertia and L, the length. And then there's two parts. It wants to know the total energy when it leaves the hand and how high it goes from the elevation of the hand, neglecting air resistance. So part A. They want us to find the energy total. So the total energy here, at least when he throws it, is, if we were to put it as generally as possible, the kinetic energy plus the potential energy. Well, if we're letting this hand be our origin, there's no potential energy. There's just kinetic energy. So the total energy is our kinetic energy, and there's two types of kinetic energy. There's kinetic energy, I'm going to just say trans. So that's your transitional. That's your energy of motion. You're moving. But there's also rotational kinetic energy, which this boomerang is rotating, so it has that. So the transitional is just like we would do before, 1/2 mv initial, because that's when we're interested in squared. Rotational kinetic energy is 1/2 I omega squared. Okay, so 1/2 mv initial squared plus 1/2, and they give us the moment of inertia as 112 ml squared times omega squared, or 1/2 mv initial squared plus ml squared omega squared over 24. And then just to remember, to make a note of it over here, omega, they said, was 10 revolutions per second. And to convert that, we know that 1 revolution is 2 pi radians. So 20 pi rads per second is the omega we want. And if you plug all that in, you'll get energy total. They give us everything else. Okay. Now for part B, it wants to know how high this goes. And an important part is it says neglecting air resistance. So because there's going to be no external forces, we have conservation of energy. Energy final is equal to energy initial. We're not losing anything from air resistance. No energy is going to be transferred into something like heat, for example. We can use this to help us solve the problem. So energy final equals energy initial. And at the peak, it's going to move. Well, I guess boomerangs come back, but regardless, it doesn't really matter. The point is, this is going to be our height y, and the only velocity it's going to have is in the x direction. That's going to be something. The velocity in the y direction will be 0, because I mean, it's the same thing if you throw a ball up in the air. If you want to know how high it goes, you want to know where it's turning back around. So at that particular moment, that's 0. So let's go ahead and work through this. The final energy, what does it have? Well, it has kinetic energy plus potential energy. Because it'll be some height in the air, there will be potential energy from gravity. To where initially, just like we said before, it's only going to have kinetic energy. And I should make a note that this is final, initial. So at the top, it only has a velocity in the x direction. So there's your transitional kinetic energy, but it's also still rotating. So plus 1/2 I omega squared. I won't change. Omega won't change either because there's no reason to. There's no external forces. Plus our potential energy due to gravity, mgy, is equal to 1/2. And I should make a note that this is final. mv x squared initial plus 1/2 mvy initial squared. So this is your transitional kinetic energy plus our rotational kinetic energy, 1/2 I omega squared. So this is your transitional kinetic energy. This is the rotational. This is all we have for the transitional kinetic energy final because of the fact that it's reaching a particular height and coming back. This is your rotational, and then this is our potential energy. So hopefully that makes sense. Well, hopefully we can see that we can cancel things. So this will cancel with this, and this will cancel with this. Okay? So what do we have? We have mass times gravity times our height is equal to 1/2 mvy initial squared. So if we were to look at the velocity, we have v initial, we have theta. Yeah, I was just making sure I was consistent with my notation. This is the y component right here. Velocity y initial is just a velocity initial sine theta by right triangle trig. So mgy equals 1/2 m times v initial squared sine squared theta. Both terms have an m, so we can cancel that. And then solving for y, we have v initial squared sine squared theta, all divided by 2 times gravity is equal to our height y. So that was just a little bit of kinetic energy, particularly with rotation. I think I've talked about transitional kinetic energy before. I don't know if I have about rotational, so figured I'd introduce that. I don't know if I've talked about inertia much, or moment of inertia much, but talked about that a little bit here, I suppose. And I'll make a few more videos. Like I said, my courses start in the fall. I honestly don't know if they're going to be online or not, so I'll try to figure that out. But in the meantime, I'll try to post some videos, so hopefully that helped a little bit solve this problem.